Welcome back. Hopefully you had a good long weekend. I was driving back from Colorado yesterday and we had snow Saturday night, so I'm driving on the ice and snow. It's 21 out.
Exciting.
And what was going through my mind?
Physics.
Coefficient of friction.
I was thinking about the coefficients of friction, especially when I saw a couple of cars that had lost control and rolled to the side of the road. I was thinking, boy, I hope that my coefficient of friction is high enough and I'm driving carefully. I hope that at some level, you're now, when you see things in everyday life, you start thinking about the physics that's going on with those things, like I was. Now, a little adjustment to the schedule. You, I'm sure, noticed that to help make sure everybody learns from exams, I went over exam questions in class on Wednesday instead of doing my normal lecture. And because of that, we're now behind on the lecture schedule by more than I consider tolerable, right? Because I'm supposed to be starting with the states of matter today. And we have rotational dynamics, which we really need to cover. So for lab tomorrow, I'm going to be doing lecture material stuff. I will have you doing some worksheet work as well. But I will be using that lab time to get us back up on schedule, because there's like, if we skip this material, that would be really detrimental to you. Well, if you're going to be taking like the MCAT or something. Okay, I need a volunteer now to pretend they're this figure skater. Okay, Andy. Now, we all know that figure skaters do their spins and stuff. Can you do this, Andy?
I can try.
No, I don't want to see you hurt yourself, so don't try. So instead, we're going to have Andy sit down. Makes life easier. All you have to do is not have your feet on the rail here, because, of course, that would stop you. And then you got to hold these things. And so she's going to be like our figure skater. As you know, the figure skater starts with her arms out here. Don't do it yet, because you can tire yourself out. Starts with the arms out here. She swings her leg out, and then she pulls everything in. So she's just going like that, right? Well, Andy's going to do this for us in a much better fashion. So now Andy's going to put her arms out like she's a figure skater starting her spin. I'm spinning her because she's not using her legs, and now she pulls them in. And what happened? She goes faster. Put them back out. She goes slower. Faster and slower, right? You saw this when you watch figure skating, now instead of being super boring, it'll only be boring. Wow. Oh, it is impressive. I will never say it's not impressive. Those people are athletes of the highest order. But it's still, I don't know, doesn't, wait, okay, you sit down. Thank you very much.
But football, that's your first thing.
Honestly, the football players are probably less athletic than gymnasts and figure skaters.
Oh, yeah, for sure.
But it's much more exciting because there's a whole much more banging into each other. When a figure skater falls, it's exciting. Okay, Russell has a statement, and then we'll get back. That's probably true as well. So we'll get back on topic. Russell.
So I think you would be one of those guys that went to gladiatorial games.
I would have, yes. Except for, no, I wouldn't have, because I hate to see people actually get hurt. I don't like boxing because people actually get hurt, Guy just died last week from boxing. So let's talk about why that happened. So using the physics terms you already know, when she's spinning around, she's holding those masses, and let's only pay attention to the masses that she was holding. What properties would you say those masses have?
Mass.
Mass. Russell is right on topic here. Besides mass, what else do they have?
They're solid.
They're moving. Yeah, they're solid. That's what I'm supposed to be covering today, not what I actually covered. The what?
Acceleration.
Okay, they were accelerating. What direction were they accelerating? Toward the center. Because to stay in a circle, it has to be accelerating toward the center. What else would you say about it? I'm looking for one of two specific things.
They were rotating.
Okay, they were rotating, which means they have Okay, well, movement, we've already talked about the centrifugal acceleration. They have momentum. That's one of the two that I was specifically looking for. Okay, you said inertia?
No, I didn't say it out loud.
Well, it came out of our lips, but it wasn't out loud. Inertia is measured in units of kilograms, right? Inertia is the idea, as is on the test, of things staying in constant motion unless the force acts on it. And the mass is the measurement of inertia. Okay, so they did have inertia.
I didn't say that.
They had, she now decides she said it out loud. Momentum is one of the two things I was looking for. They have momentum. Now, as they're rotating, the direction that momentum is changing, so the momentum is constantly changing, right? But they have momentum. So that momentum is going to make it so the motion is a little harder to stop, right? Because more momentum, harder to stop. Less momentum, easier to stop. Now, of course, I said we're ignoring her body. Her body had momentum as well. Each part of her body had momentum. Those had momentum. When you calculate momentum, what's the equation? Momentum is equal to blank times blank.
Mass times velocity.
Mass times velocity. So we would have to take each piece of mass that makes up her and makes up those two things. That's why I said let's just look at those two things at first. And we'd have to say, well, we have this mass, its velocity is, well, it depends on what the radius is, what the velocity is. And so it's, if we stick with angular velocity, omega, then we can say the velocity is omega at r. And so the farther out it is, the bigger the speed by that r. And so then we would have to add up all of the pieces. How do we do that? Addition. Unfortunately, when they're continuous, we have to have a special math that Newton invented for adding up things that are continuous that we call calculus. We have to integrate. We're not doing integration here. Instead, we use a term that is moment of inertia. So keep in mind, inertia and moment of inertia are two different things. Moment of inertia, which I don't know if you guys have talked about it or not in your statics class. Probably not, because your statics doesn't matter. The moment of inertia is the rotational equivalent to inertia. So inertia was measured in kilograms, and it's telling you about the resistance to change in motion. Moment of inertia is actually measured in kilograms times meters squared, and it's measurement of the resistance to change in rotation. So it's fundamentally the same idea, but one's in rotational form. Why does it have the distance part? Because the speed depended on what the distance was. And so in the calculations, it comes out to have radius squared. So in a general sense, we have the moment of inertia. I took out 3 slides because I decided to talk about all of it on this one slide. So we have I is equal to the mass times the radius squared. What's the radius? It's the distance from the axis of rotation. So now, in Andy's case, when she held the masses out at arm's length, where was her axis of rotation? Straight down through the head, right? And so the radius is the distance from that line straight down through the head out to these masses. Where do you choose to measure from? If you have a line you're measuring from, where do you choose to measure from? Okay, well, the closest point. The point where you're measuring perpendicular to that axis. And so the radius was out here. Okay, for me it's about, let's say, 80 centimeters. Now if I bring them in here, what's the radius? Not so much. It might be 10 centimeters. So if I went from 80 centimeters to 10 centimeters, how much did that moment of inertia change by? It's mass times radius squared. 80 to 10, it went from the mass times 80 centimeters squared to the mass times 10 centimeters squared. It's easier to talk about the ratio. If I do the ratios, then the masses cancel. And I just have radius 1 squared over radius 2 squared, which would be either 1 over 16 or 16 over 1. Okay, I obviously went to centimeters to, or tens of centimeters there in my head. So it would be 8. Anyway, 8 and 1. So you'd have, it turns out, 8 squared is 64. So the difference in the moment of inertia was 64 times. Now, what did it take to change your momentum? According to Newton's second law,
External forces.
an external force. Notice I did not let her have her feet sitting on the rail, because that would have provided something to change her rotation. If the bearings were perfect, there would be nothing to change her rotation, right? You just keep spinning forever if you're just sitting there spinning, if the bearings were, and there's no air. So in rotation, what are you supposed to be equivalent to a force is? We've actually talked about it, but I want to make sure it's clarified now. Know that question? Remember my dad's story?
Oh, torque.
A torque, that's right, a torque. A torque is the rotational equivalent. So if there's no torque about the axis of rotation, then your angular momentum about that axis will remain the same. And the angular momentum, well, linear momentum is mass times velocity. Angular momentum is the rotational equivalent to mass, which was the moment of inertia, times the rotational equivalent to velocity, which is the angular velocity. And so we have the angular velocity is omega. I is the moment of inertia. Remember, I wrote I equals mr squared. I don't know if I made it clear. I stands for moment of inertia. Oftentimes people make the mistake of saying inertia because the symbol is I. But what is inertia? It's the mass. If you want to be all technical like, you have mass has two definitions. There's the gravitational mass and the inertial mass. But they're the same thing as far as we can tell. So we only talk about mass. So L, what is L then? M is mass, I is moment of inertia, L. Okay. I've used the words, but I haven't talked about the symbol L, but it's angular momentum is what L stands for. Why L? I don't know. It's probably just as good as the reason why we use P for momentum. So angular momentum is moment of inertia times angular velocity. And so with our example with Andy, when she brought those masses in, the moment of inertia dropped significantly, but there are no external torques to change her angular momentum. So the angular momentum had to stay the same, L had to stay the same. If I goes down and L stays the same, what happens to omega? Goes up, so she spun faster. Now, I forgot the test in my office, so I'll be right back. We're going to take the post-test, the same test we took in lab, the first lab period of this semester. So go ahead and get ready to take that as I bring them in.
This is not good.
This is great.
This is great.
So the first one is extra credit, right?
The first one, yeah.
So this one's extra credit too then? Oh my God. Give me that one. The final. You gotta move the test.
We don't have to process.
And just like the first time around, this is for a small amount of extra credit.
We're always.
And remember, do not write on these test forms. And we have until the end of it. Well, actually, I have still 5 minutes before it's time to start. So I have time to hand things out. So, yeah.
Oh, boy. So we have homework?
No, we won't have an additional homework because we didn't have enough lecture. But, well, I say we won't. I will be lecturing in class.
So we'll have.
I'll be lecturing in lab tomorrow.
Do you have to do a lab?
Pre-lab quiz.
Pre-lab?
I will not count your grades. You do not have to. At the same time, it's a good check-up unless you have questions of the procedural way. How many classes?
Okay.
But I won't be grading. Which is good. Or,
Wait, so are you done lab tomorrow?
We're coming to lab, we're not doing lab. We're just doing
Another assessment test.
Okay, and you can use pen or pencil to record your answers on these forms. So when I give you these Scantron forms, you go ahead and get started.
She's on those.
So this is the same thing as
This is part of the reason why you can't take them home.
If they need to be selling books or cleaning, I like that.
And of course, this is very important to me because it's a standard measurement of what you've learned so far. Guess you're the last one. See if I can get this cut. Taking it by hand. Sorry. I can go this one. And I'm sorry, it's uncomfortably warm in here.
Are we still assuming no air resistance for all of this?
Yes, assuming no air resistance for everything. And unless it specifically mentions it. Okay. So for number 3, it doesn't say assuming air resistance, but there is air resistance based on the answer options.
What about 1 and 2? Yeah.
Let me look at 1 and 2. No, number 1 and number 2 assume no air resistance.